Good morning. Well, it could be even by the time you're seeing this, but we are going to cover continuity and one-sided limits. First thing we want to look at is three types of graphs. The word continuity, its base word is continuous, so I think you understand what continuous means. If we look at these three graphs, we can see that for each of them, there is a place where the function is discontinuous. Clearly, from the open interval a to b, we can see that f of c is not defined. C and f of c not defined. That point's missing. Here, if I look at the limit as x goes to c, remember that when we say the limit as x goes to c, we mean from both sides of it. The limit does not exist. So we have some discontinuity here. And if I look at this one here, the limit as x goes to c clearly approaches this y value L, so the limit exists, but it is not equal to the y value when x is c. So the limit is not equal to f of c. So these define issues concerning continuity. So continuity at a point. A function f is continuous at x equals c if the following conditions are met. 1, that f of c is defined. 2, the limit as x goes to c on f of x exists. And the biggie for today, that the limit equals the y value when you get there. The limit as x goes to c of f of x equals f of c. Let's remember when we say the limit exists, that means when we are approaching from the left side and right side of c, that those values are equal. Open on an interval. F is continuous if it is continuous at each point in the interval everywhere from negative infinity to infinity. So we can talk about various discontinuities. Up here in this graph, we had a removable discontinuity. Removable because a point has been removed from the function. So the limit exists, but f of c is not defined. This function could be made continuous by defining or redefining a point by filling in a hole. Graph 2, we have a jump. I come this way and I have to jump to get down here. So that is a non-removable discontinuity. It has a break or an asymptote or a jump. Graph 3 has a hole like the first one that could be filled in by that point. So it looks like this point here was just taken out of the graph. So that is a removable discontinuity. A point has been removed. So discussing the discontinuity of each of these, look at 1 over x. F of x equals 1 over x. We know that the graph looks like this. And we can see we have a vertical asymptote. When x is 0, we call that a non-removable discontinuity. Now let's look at the function g of x is x plus 3 over x squared minus 9. We know that this denominator will factor since it's a difference of two squares. And our factor in the denominator will cancel with the 1 in the numerator, leaving this function 1 over x minus 3. So that means g of x is going to look a lot like this one, 1 over x minus 3, except it's going to have a hole when x is negative 3, because that is where we canceled this factor. So we have a hole, which is a removable discontinuity at x equals negative 3. And look at this. We still have a vertical asymptote at x equals 3, and that would be a non-removable discontinuity. If we look at the function h of x equals cosine of x, there's no discontinuity at all because that function is continuous. One-sided limits. These are limits when you can only take the limit from one side. For instance, let's look at y equals square root of x. You know what y equals square root of x looks like. We can only approach 0 from the right side. We can't approach 0 from the left because x cannot be negative. And let's look at y equals natural log of x. We have a vertical asymptote here because x can never equal 0 because there is no number. A logarithm is an exponent. There is no number I can raise to a power and get 0. So we can here, again, only approach 0 from the right side. So there are times when you can only approach from one side. The greatest integer function. This is our symbol that refers to the largest integer, which is not greater than or not to the right on the number line, the quantity inside. For instance, if I looked at the greatest integer of 1.5, well, 1.5 lies here, and the greatest integer is 1. 1.5 is on this piece. The greatest integer function is the biggest integer not greater than what's inside of there. Well, 2 is bigger than 1.5. So when x is 1.5, the biggest integer not bigger than 1.5 is 1. When I get to 2, I jump up to this piece. So the greatest integer of 4 is 4. The biggest integer not bigger than 4 is 4. But then it's crazy when we get over here to negatives. All right, so where is negative 2.5? Well, negative 2.5 falls in this piece. When I go from negative 3 to negative 2, I just added that piece in there. Negative 2.5 is right here. And the biggest integer not bigger than negative 2.5 is actually negative 3. Now, if I look at 2.5, that's over here. The biggest integer not bigger than 2.5 is 2. This is a function that has a lot of practical uses. You're not going to use it a lot in calculus, but that's what that symbol is. And let's just think about when you go park at a parking garage and you have to pay. And let's say that it's $1 for every 15 minutes. So even if you're there for 5 minutes, you're still going to pay that $1. But when you're there for 16 minutes, it jumps up to the next $1, even though you've only been there 1 minute longer than that first time interval. Or mailing letters. Now, I know you probably don't do that very often, but there are weights, a certain amount of weight, and it gets a price. The next, over that weight, it jumps up to the next price. So the greatest integer function has jumps. Okay. Absolute value, evaluating limits involving absolute value functions. If we say the absolute value of 5 is, we know that that's 5, but we need to think about this in a little bit different way. If the quantity inside the bars is not negative, then the absolute value of that quantity is that quantity, or is itself. So let's think of it this way. If the quantity inside the bars is not negative, then the absolute value of that quantity is itself. Now, what happens if I have a negative 5 inside of here? If the quantity inside the bars is negative, then the absolute value of the quantity is the opposite of itself. You can say the absolute value of negative 5 is 5 because everything's positive, but a better answer is that absolute value ensures that your quantities are positive. So if we have a negative in there, in order to ensure that that becomes positive under the absolute value function, we have to negate that thing that was negative. Now, this is going to be important when we get to piecewise functions. So here we're going to write the function f of x equals absolute value of x minus 2 as a piecewise function. Well, finding it as a piecewise function, since it's absolute value, we need to figure out where the quantity inside the bars is positive and where the quantity inside the bars is negative. Well, that involves finding where the quantity inside the bars is 0. So we're going to be looking at numbers greater than 2 and smaller than 2. Now, this is very elementary for you, but we know that when numbers are bigger than 2, the quantity will be positive. And when numbers are smaller than 2, the number quantity will be negative for those numbers. And so 2 is our dividing place. The absolute value of x minus 2 will be what? X minus 2 when x is bigger than 2. And the opposite of x minus 2 when x is less than 2. So when x is less than 2, the absolute value of x minus 2 is the opposite of x minus 2, because when x is less than 2, when we approach 2 from the left side, this quantity is negative. Absolute value bars tell me I have to have everything not negative. Not everything positive, everything not negative, because 0 is neither positive nor negative. All right? When x is greater than 2, or when we are approaching 2 from the right side, my quantity inside the bars is going to be positive, so the absolute value of something when it's positive is itself. Now, this is a very important way to work with absolute value functions. You need to think of it like this. Trust me when I say this, things will be coming throughout the year that you need to understand that kind of quantity. So we're going to determine whether this function above is continuous at x equals 2. What does it require for continuity to happen? Well, the limit from both sides. So when we say continuous, that means the limit as x goes to 2 on our function must equal f of 2. The limit has to exist, and that y value we're getting close to must be the y value when we get there. Okay. So let's start with f of 2. F of 2 is 0. All right, so now if this function is continuous, then when I approach 2 from the left and right-hand side, I'd better be approaching 0 for continuity to occur. So let's look at the limit as x goes to 2 from the left on our function. That's the limit as x goes to 2 from the left on our function is defined like this for values of x going to 2 from the left. So I'm going to write that part of the piecewise function here and then evaluate it. I get 0. Yay. Now let's go for 2 from the right. That's this piece right here. And 2 from the right gives me, yada, 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 0. So the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. So the limit exists. And that limit equals the y value when I get there. So our function is continuous. And here is a very, very important definition, very important. A function f is continuous at some c if, as x goes to c from the left on the function, that is equal to as x goes to c from the right on the function equals the y value when you get there. Properties of continuity. If b is a real number and f and g are continuous at x equals c, then the following are also continuous. I can take the function and multiply by a scalar. I can take my two continuous functions and add them or subtract them. That will also be continuous. I can take my two functions and multiply them. That will be a continuous function. I can take my two functions and divide them. That will be continuous except for where g is 0. So g cannot be 0. Continuity of composite functions. If g is continuous at c and f is continuous at g of c, then the composition f of g of x, which is also written as f of g of x, will also be continuous at c. Let's remember a little bit of notation. At c, the y value on g, g of c, is a point on g of x. Let us remember that g of c now becomes your x value on f. Find the value of k that makes h continuous. Now, h is a piecewise function, and h is defined as x squared for values of x less than 2, and as k minus x for values of x greater than or equal to 2. So how do I talk about continuity? The limit has to exist. The limit as x goes to 2 from the left has to equal the limit as x goes to 2 from the right. And not only does it have to exist, it has to be the y value when you get to 2. So let's look at things. We need to first of all see if we can find the limit as x goes to 2. Well, when x goes to 2 on function h, the function to be used is k minus x, because that is when x equals 2, we have to use this. So we are looking for k, and since we're doing that, we have to use the other function to find the limit. So this function is going to be, this piece is going to be what we look at as x goes to 2 from the left. So I'm going to use that function from the left, and that y value is 4. Well, for the function to be continuous, the limit has to exist. So if the limit from the left is 4, then the limit from the right has to be 4. So the limit from the left on my function has to equal the limit from the right on my function. Now the limit from the left on the function is 4. The limit from the right has to be k minus, as I get close to 2, k minus 2. And now you can solve that for k. And now let's rewrite our function since we have found the value for k. So we're going to rewrite h of x is x squared when x is less than 2. That wasn't a problem. But now that we know k, it is 6 minus x when x is greater than or equal to 2. Therefore, when k equals 6, the function will be continuous, and we can confirm that by substituting 2 into this piece, and we do get 4. So we would say the limit as x goes to 2 on our function h of x equals h of 2. So h is continuous when x is 2. All right, your very first existence theorem. There are a few of them, and they're very important. The intermediate value theorem, IVT, intermediate value theorem. Intermediate means between. Think about middle school is called, in some places, intermediate school. That is because it is between the elementary and high school level, between. So if f is continuous on the closed interval from a to b, and k is any number between f of a and f of b, in other words, k is a y value between the y value at a and the y value at b, then there is at least one number c in my interval from a to b such that f of c is this y value k. It's an existence theorem. Why is it called existence? Because it shows you that it exists. It doesn't tell you how to get it. But let's do a nice little example. It says here we're going to use the intermediate value theorem to show that there is a 0, in other words, f of x equals 0, in the interval from 0 to 1. Notice that's a closed interval for this function. So I want to know, is there some place where this thing equals 0? Since f of x is a polynomial function, we know from what we learned in the last section, it is continuous. So now I want to find f of 0, substituting 0 for x, I get blah, 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 -2. And I want to check the y value at the other endpoint, f of 1, and we get 2. Do you agree that somewhere between -2 and 2, there has to be the value 0? So, since f of 0 is negative and f of 1 is positive, the function must cross the x-axis between 0 and 1. Therefore, there is some c in the closed interval from 0 to 1 such that f at c equals 0. You will use this in weird places throughout the year. So make sure you know this theorem. So your TPs for section 1.4 are numbers 3, 11, 25, 39, and 45. Have fun. I'll see you next time.